Hey everyone! So we're back for another lesson on fractions today, and we're going to jump right into it because, well, we got lots to get through in this one. So we're just going to do a quick review to start this one off about what we did last time. Sorry if I was sort of jumping around a little bit in the last lesson. I've been doing so much stuff with fractions recently that it's just all kind of mixed up in my head, and I didn't want to say too many things and mention too many things that you don't have to worry about all at the start of the fractions and decimals unit. But anyway, basically to recap what we did last time, we talked about what fractions are, when we use them, why they're useful. Not extensively, but enough, hopefully, to give you guys an idea of why this is something that's important and useful, at least to a certain degree, in everyday life. Like last year we were doing stuff with trigonometry, and the year before that there was stuff with differential equations. Not everybody's going to be working with that kind of stuff, once they're out of school, and depending on the type of job you get, that might not be something that you interact with every day. But things like fractions and decimals and the multiplication and division we've been doing, some of the stuff that we're going to see in the not-so-distant future, is stuff that you're going to use on a daily basis or on, relatively frequently in your life. So hopefully this concept isn't coming across as too alien to you thus far. But so just a quick review. From last time, we were talking about proper and improper fractions. So those are two different types of fractions. Proper fractions are those where the numerator is smaller than the denominator. Remember that the numerator is always the number on top, denominator is always the number on the bottom. And so because the numerator is smaller than the denominator, that's representing parts of a whole. If the whole is made up of 3 parts and you only have 2 of them, then you always have less than one whole, right? So basically, if you have a proper fraction, you always have less than one complete whatever you're talking about, right? We frequently talk in terms of like pizzas and pies, things like that, things that we interact with that are divided into sections, and it's not always halves or quarters. Sometimes it's eighths or twelfths, things like that, right? So if you have a proper fraction, the quantity that you're dealing with is smaller than 1. And we'll see that a little bit later. When we start converting fractions into decimals, a few lessons from now, you'll see that all of these proper fractions, when you turn them into decimals, they're all going to be numbers between 0 and 1. They're all going to be 0 point something something. And then we talked about improper fractions, which are similar in how you write them, except the numerator is now bigger than the denominator. I meant to write that one upside down, but we're going to make it an actual improper fraction. You could do, almost anything, and your options are endless. It's not like there's only a handful of proper fractions or only a handful of improper fractions. So lots of different things that you can do with them. And we also talked a little bit about reducing, which we're going to get back into a little bit later. But first I want to introduce, we sort of talked about it just briefly at the end of the last lesson, but I want to introduce the third main type of fraction that we're going to be dealing with, and that is the mixed fraction or mixed number. You can call it what you like. I've been calling it mixed number more recently, so I've written that here. Before I continue with that, remember that with improper fractions you can have that special case where if the denominator is 1, then you are dealing with a whole number. So with proper fractions, if the numerator is 1 and the denominator is whatever, that doesn't mean particularly much. That's not necessarily an overly useful thing to be working with. With improper fractions, if the denominator is 1, that's the same as just dealing with the whole number itself. So you're not dealing with any parts of, or like incomplete pizzas, for instance, right? You'd be dealing with 3 full pizzas if you had 3 over 1, like that. But anyway, back to mixed numbers. I'm going to change that back to a 2. Mixed numbers are those where you have more than one whole. So just like improper fractions, we've got more than one pizza, if you will. And you, instead of expressing it like this, what we've done when we write it as an improper fraction is we're basically expressing that instead of saying I've got you know, this many complete pizzas that nobody's touched and then this many leftover slices from another one, we just straight up, we just say, you know, I have this many slices of pizza available, and each slice is, for instance, if we take the 17 over 12 here, you'd say, all right, well, I've got 17 slices of pizza, where each slice is 1/12 of the pizza. That's what you're basically conveying with an improper fraction. But with a mixed number, what you do is you take that and you say, okay, well, I've got 17 slices here, and each one is 1/12 of the pizza. So I could take 12 of those slices and make a whole new pizza. So you could write that as, I've got one entire pizza, and then I've got a few slices left over. So a mixed number will always look something like this, that you have this large whole number sticking out on the left side, and then you also have a fraction attached to it. So it's like you express how many complete things you have, pizzas we've been saying, so it tells you how many complete things you have, how many complete pizzas or whatever, and then also how many incomplete pieces you have left. So it's like if you had 2 pizzas, 2 entire pizzas, and then you had 7 slices left out of a pizza that was originally cut into 8, well then you could write it as a mixed number where you say you have 2 whole pizzas and then you've got 7 slices out of a pizza that was originally 8 slices. So you could express that as a mixed number. Now what we're going to do in the rest of this lesson, we're going to go through a couple more reducing examples, which is what we were doing yesterday, or hopefully yesterday, depending on when you see this, what we were doing last lesson. And then we're going to take that one step further and sort of dive into the relationship between improper fractions and mixed numbers, because they represent the same idea, right? They both represent having some complete parts and some incomplete parts. So like some entire untouched pizzas and then some just extra slices of a pizza. So they're both representing similar ideas, whereas with proper fractions we're not dealing with any whole pizzas, we're dealing with only portions of a pizza. So we're going to explore that sort of relationship and how to turn a number from being in this form to being in that form a little bit later on. But first what we're going to do is we're going to go back to some examples of reducing fractions. So reducing is useful. It can be a little bit complicated sometimes, but once we get into, in the next lesson, or probably the next lesson after this one, once we get into adding and subtracting fractions and then later multiplying and dividing, you'll find that this stuff, this reducing stuff that we're going to do in this lesson, as well as the mixed number stuff that we're going to be talking about a little bit later, is going to come in really handy. So if you remember our example from last time, just really quickly, it was something like 9/27? Yeah, so we had 9/27 last time. And what we did is we basically looked at that numerator, we looked at that denominator, we thought, okay, what's a number that I can divide both of those quantities by? I don't know if you can see that division sign particularly well, hopefully that's a bit better. And then same thing down there. And so we thought, okay, what can I divide both 9 and 27 by that still gives me a whole number? And so, you know, you could divide it, you don't have to necessarily divide it by the biggest thing possible if you don't happen to notice it. It's not a big deal. Last time, I believe, we just right off the bat, we thought, oh, okay, 9 and 27 are both divisible by 9, so we just kind of went ahead and did that. But if you don't happen to notice that, then you could divide by something smaller that still works, right? You could divide 9 and 27 by 3. Maybe you notice that more easily. So then you go ahead and you do that. You get 9 divided by 3, leaves you with a 3 on top. And then 27 divided by 3 leaves you with 9 on the bottom. And as you can see, there's no real harm done, because now we can just look at our new fraction over here, and we'll notice again, oh, I can just divide both of those by 3 one more time. And so that leaves you with 3 divided by 3, which is 1, and 9 divided by 3, which is 3, which, if you remember, this is the answer that we got last time. So basically, what you end up doing, if you did it the other way, if you happen to do it just right off the bat, you look at that 9, you look at that 27, you see they're both divisible by 9, so you just go ahead and do that right away, you get that 1/3 as well. Now what you might notice, and this is where stuff from our last unit is coming in handy, is that 9 is the highest common factor of 9 and 27. So if you can find that highest common factor between two numbers like this, you can just reduce those in one shot. I mean, it does take some work to find the highest common factor, but once you have it, this reduction from 9/27 to 1/3 happens in one step. Otherwise, you might have to do it in pieces, and when you're dealing with bigger and bigger and bigger numbers, you kind of get stuck if you're doing it in chunks like that. You know, if you're dealing with numbers in the hundreds and numbers in the thousands, it might just be easier to find that highest common factor and divide by that, because otherwise it'll be like that list thing that we were doing with LCM and HCF, which is where you try and list all of the factors, just, you know, trying to figure out, oh, okay, 2 times 8 gives me 16, but so does 4 times 4, and so does, you know, you end up just listing all of them. It takes a long time, there's a chance you missed something, you know, it leaves the door open for mistakes, or just for things taking a lot longer than they could have otherwise taken you. So that's where some of that HCF stuff comes into practice. Now with smaller numbers like this, you might not have to go and actually calculate the HCF in your head. It's just a matter of noticing that 9 and 27 are both divisible by 9. But what you're really kind of doing behind the scenes is you're finding that factor, that common factor between both of them, and in this case where you divide both of them by 9, you happen to have found the highest common factor, whereas up here you just found a factor, a common factor, which was 3, and then another common factor, which was another 3. Alright, so now we're going to do a new example for this one. And it's going to be, instead of a proper fraction, we're going to deal with an improper fraction this time. So we're going to make the numbers significantly larger so that this gets a little bit harder. So we're going to try and reduce 52 over 28. So basically what this means is, if you were trying to do it in maybe the context of a word problem where you've got, you know, 52 chocolate bars and 28 friends, first off, that's a lot of friends, but you could describe this fraction as 52 divided by 28. That's a perfectly valid way to go about this. But if you were working with fractions and you happen to write it this way, you want to express this in its lowest possible terms. And what that means is basically you want to reduce both of these things down by dividing them by their highest common factor, ideally, until you get to two numbers that don't have any common factors other than the number 1. So basically you want to take this 52 and chop it down into smaller and smaller pieces, so that maybe you get something like a 10 or a 12, you know, numbers that are smaller to deal with, or if you're lucky, numbers like 3 or 4 or 2 or 1, things like that. Now with an improper fraction, you're not going to get a 1 on top, because that means you would have a decimal on the bottom, right? Since this one on top has to be bigger than that one, since, you know, it's already bigger than that one. But we don't like decimals in our fractions. So for an improper fraction, you're never going to get a 1 as the numerator when you reduce it, and same with proper fractions, you're never going to get a 1 as the denominator when you reduce it all the way. So what we're going to do here is, there's two ways you could go about it. One is trying to find the HCF of 52 and 28, and what I'm actually going to do is I'm going to leave that as an exercise for you guys to try. So if you have some spare time, you know, when you're at home in the evening and you've got nothing to do, and you're all just watching TV or on the internet, you know, take 5 minutes and see if you can do this problem by finding the HCF of 52 and 28, and then just once you find that HCF, you'll divide both of these numbers by whatever that number is, whatever that highest common factor is. I'm going to do it a different way, which you'll see is far less efficient once you go and do it that way, with the HCF way, which is I'm just going to look at these two and just guess a number that I can divide both of them by. And so if I look at both of them, I see 52 is even, and I see 28 is even. So if I just go through and I divide both of them by 2, since they're both even, that's perfectly valid. I can divide 52 by 2, I can divide 28 by 2, and what that's going to leave me with is on top I'm going to be left with a 26. Right? 52 divided by 2 is 26, and on the bottom I'm going to get 28 divided by 2, which is 14. Now, this might not seem like it's taking a while because, well, one, I worked out these solutions earlier, but even then it didn't take that long. But that's because, you know, if you're comfortable with dividing numbers like 52 by 2, then yeah, no problem. You'll get to this step really quickly, and then you'll see, oh, 26 and 14, both still even numbers. Let's just divide them by 2 again. And you can keep dividing by those small numbers, small prime numbers even, perhaps, until you get to something that's more manageable, more bite-sized in terms of the numbers that you're dealing with. So since they're both even, I can divide them by 2 again. 26 divided by 2 is going to give me 13, and 14 divided by 2 is going to give me 7. And 7 and 13 are both prime numbers, so that's the most reduced that I can get this particular question. Now, make sure you keep that 13 over 7 kind of in the back of your head, because we're going to pull it out again in a few minutes. But basically, if you look at it and you just guess numbers that you think might work, that will technically work in practice, but it can take a really long time. You know, if you're dealing with numbers like, I don't know, like 1024 over 4096, you can reduce that a lot. You can reduce that down to 1 over 4 if you try. But if you're going to do it by just dividing them by 2 or dividing them by 4 over and over and over again, you're going to be there for a while, and you're going to be doing lots of division. And if you can't do that division in your head of 4096 divided by 2 or divided by 4, you're going to be doing a lot of long division on the side of your page just to get an answer of 1/4. Whereas instead, you could be looking at the 1024 and the 4096, finding their highest common factor, and then dividing both of them out by that highest common factor. And so, sure, it takes a little bit of work to get that highest common factor, but when you're finding that HCF, there's more multiplication and not very much division necessarily. You could argue that, well, you know, you have to do a lot of division when you're finding the HCF, but it makes this reduction from two enormous numbers to a smaller, much more manageable fraction a lot less steps. It takes up a lot less space on your page. You know, there's justification for reducing fractions in as few steps as possible, and it might save you time on a test. But if you prefer to just look at it and guess, then that's valid too. It just might take longer in some situations. But so far, no problems. We took this 52 over 28 and we chopped it down to 13 over 7. And so ultimately what we really did was we divided by 2 and then divided by 2 again. So effectively we have divided both the numerator and denominator by 4 is basically what we've got. And so we got 52 divided by 4 gives us 13, and 28 divided by 4 gives us 7. So that gives us that fraction over there. I'm just going to throw it up here in the corner because we're going to revisit it in a few minutes' time. But before that, we're going to do one more reduction example, one more case of reducing fractions. And so for that one, we're going to start with an even larger number as the numerator. We'll start with 134, and we're going to divide that by 24. And we want to get that in its lowest possible terms. So for this one, once again, if you want, you can go through and you can try and find the HCF of these two numbers. It shouldn't be that hard. It's only two numbers, right? With our fractions, we're not necessarily going to be dealing with, 3 or 4 or whatever. We're only dealing with the numerator and the denominator, so it shouldn't take that much effort to go and actually find the highest common factor. But if I want to take the way that at least looks easier, kind of at face value, I'll just notice that, okay, 134 and 24 both end in a 4, which is an even number, so they're both divisible by 2. You could also always check your divisibility rules, see if they're divisible by 3 or 4 or 6 or something like that. 24 is divisible by 3, and it's divisible by 4, and it's divisible by 6, but when you go and you check your numerator, those don't all necessarily work. So you could try and find, oh, is it divisible by 3? And you add up the digits and you'll see that it's not. Is it divisible by 4? Last two digits aren't divisible by 4, so it's not. And so you can sort of rule out some of those other things. So in this case, it actually seems like our best option is to just divide both of them by 2 and then see what we're left with. And so if we divide both of them by 2, we divide 134 by 2. That might take a little bit of work, and you might want to work it out on the side of your page. But what you'll find is that 2 doesn't go into 1, but it goes into 13 6 times. So that leaves us with 12 down there. We subtract, we get a 1, bring down the 4, and 2 goes into 14 7 times exactly, which leaves us with a 0 at the bottom as our remainder. And so what this means is that 134 divided by 2, that's going to give us 67 as our new numerator. And then for our new denominator, we're going to get 24 divided by 2, which is going to leave us with 12 down there. Now here, you might not recognize, is 67 a prime number? Is it divisible by 3 or 4 or 7 or something weird? Kind of tough to tell. It's not a number that we deal with every day when we're doing more basic math. And so what you can do is you don't have to go and look at the factors of 67 to see, oh, is it divisible by this or that or the other, or is it prime, is it not prime? You can look at the factors of 12, and just because it's smaller, it's going to have less factors. So if you look at the factors of 12, this isn't like a prime factorization thing, but if you look at the factors of 12, you'll get that, well, 1 is a factor, and you'll get that 12 is a factor, and you'll also get that 2 and 6 are factors, and you'll get that 3 and 4 are factors of 12. So you can check your divisibility rules for 67 using these as your test cases. We don't really care about the 1, so we can sort of ignore that, and we'll focus on the rest of them as sort of our test cases to see, is 67 divisible by any of these? Well, it's not divisible by 2. It's not an even number, so it's not divisible by 2, and that also means it's not divisible by 4 or 6 or 12, since they're also even numbers. So our only hope is it divisible by 3? And if you go and you add those digits together, 6 plus 7 is going to give you 13, which is not divisible by 3. So it's not divisible by anything useful. We don't actually care. Is it prime? Is it composite? Doesn't matter to us. All that matters is that it's not divisible by the same things that 12 is divisible by, right? So you don't have to memorize, oh, is 67 a prime number? Is 73 a prime number? Is 97 a prime? You don't need to know those things. If your denominator is like 4 or 5 or 7 or 11, you only need to know the factors of your denominator and then just test those with the numerator, assuming that the numerator is your larger number. If you're working with like 8 over like 123, you don't need to know, oh, is 123 a prime number, a composite number? You can just do a couple of tests. 8 is only divisible by a few things. It's divisible by 1, 8, 2, and 4. So you can just test those. If it's not an even number, it's not divisible by 8, 2, or 4, and that kind of gives you your answer. Right? That tells you if you can reduce it anymore, or if you're kind of stuck with what you got. So with this 67 over 12, because it's not divisible by any of the same stuff, we just say that that's our final answer. We get 67 over 12 is the most that we can reduce 134 over 24. So what I'm going to do is I'm going to take that 67 over 12, I'm going to throw that up there as well. We're going to revisit that shortly. So that's just a couple of examples of reducing fractions. The next thing we want to do is we're going to go back to that thing with improper and mixed numbers, and we're going to convert them. We're going to convert them from one form to the other. Sometimes one is more useful than the other, so you should know how to switch between the two. So we'll start with improper fractions, and we'll start with a small one, a relatively easy one, like 4/3, and we want to convert this into a mixed number, or a mixed fraction. So the way you can think of this, 4/3, the way it is right now, is that you had a pizza that was cut into 3 slices for some reason, and then you had a second pizza that was cut into 3 slices. So 4/3 means you ate 1, 2, 3, and 4 slices of pizza. So if you draw it out in a diagram, we've colored in 4/3 of the pizza, right? Each of these segments is 1/3 of the pizza, all the way around for both of them. And so we've eaten 4/3 of the pizza. But if you wanted to write this as a mixed number, you can see that we've eaten one entire pizza over here. So you could write this as a mixed number with a big 1, and then ask yourself, okay, after I take away all the complete pizzas that I've eaten, what am I left with? And so that's what we have over here. That's the incomplete pizza, the one where we ate just a portion of it, but we didn't eat the entire thing. And if you look at that one, you get that, well, we only ate 1 slice of the pizza, so we'll have 1 as our numerator, and then the pizza is still cut into thirds, so that denominator stays the same. And so what you get is that this conversion from improper to mixed for 4/3 is that 4/3 is the same as 1 and 1/3. And so you'll notice that the denominators stay the same in both cases. There might be the occasional problem where, you know, you get an improper fraction that's not been reduced to its lowest terms. So then you got to reduce it first, or you can convert it to a mixed number and then reduce that. We'll get to more examples of that stuff a little bit later on. But one thing you should note is that this denominator is the same for both of them, provided that they're both in lowest terms, or basically reduced form. And they convey pretty much the same information. If you wanted to convert an improper fraction to a mixed number without drawing the diagram, you know, if you're working with huge numbers like the 134 over 24 or something, that's a lot of pizzas to draw, and that's not a very easy diagram to make and to color and to keep track of. So the way you can think of it is, if you have that 4/3, that you ate 4/3 of the pizza, basically you look at your denominator and you had your 4/3, so you look at this 3 and you say, all right, how many times can I fit this denominator into that numerator? And you get, okay, so basically how many times does 3 go into 4? Well, 3 goes into 4 once. No problems there. Now, if I put 3 into 4 one time, that's basically me saying 3 goes into 4 once, 3 times 1 is 3. So if I took away 3/3 to create a whole, so I had 1/3 over here, I had 1/3 over here, I had 1/3 over here, and I take all of those away so that I can make one whole pizza. Out of those 4/3, where I've got, you know, that 4th third of the pizza sitting over there, out of those 4/3, if I take 3 of them away to make that one whole, what am I left over with? How many thirds of the pizza am I left over with? If you take those 3 away to make that one whole over there, then you're only left with this 1/3 of a pizza down here. And so that becomes the fraction component of your mixed number. Alright, is that making sense? Hopefully that's making sense. What we're going to do now as long as, I think that's everything I really needed to cover, so that you get an idea of how this converting improper fractions to mixed number thing really works, and without being super dependent on the pizza analogy, we're going to get rid of that, and we're going to pull out those improper fractions from before. We're going to start with that 13 over 7, and we want to convert this into a mixed number. So what you can do, here's another way that you can sort of think about it, is, so we ask ourselves, you know, how many times does 7 go into 13? And if you're sort of struggling with that, what you can do is you can break this up. If you already look at it and you say, okay, you know, 7 goes into 13 this many times, that's fine. But if you can't see that, then what you can do is you can break this 13 into groups of 7 until you're left with a number smaller than 7 as your numerator. So basically you take this 13 and you say, okay, well, if I've got 13 sevenths, then that means I can make 7 sevenths and I'll have something left over. Right? If I take 7 sevenths away from this 13 sevenths, that's like you had a pizza cut into 7 slices, and you had a couple pizzas cut into 7 slices, and you ate 13 slices in total. So it's okay, I can say, okay, 7 of those slices were, you know, Hawaiian or something, and then I'm going to have something left over, which is also still going to be some number of sevenths of the pizza. I know we're still talking about pizzas, but in the next one, it's really going to be hard to start thinking about this in terms of pizza slices. So if you take that 13 and you break it into groups of 7, you'll find that you can only fit one complete group of 7 in there before you start to run out, because as soon as you take 7 away from that 13, you're only left with 6. You can't make another whole group of 7 over there. So you're left with 7 over 7, or 7 sevenths, plus 6 over 7, or 6 sevenths. And so this 7 over 7, remember that these fractions are the same thing as just dividing the top number, the numerator, by the bottom number, the denominator. So we get that 7 divided by 7 is just 1. So what I can actually do is I can replace this 7 sevenths with a big 1. Right? And then I've got 1 plus, and I'm left over with 6 sevenths over there. And you see that this is starting to look more and more like a mixed number. The last step is to just remove that plus sign, and you get your mixed number. You take the number of holes that you can fit. How many times does this denominator go into that numerator? Becomes your whole number. And then whatever you have left after you take away all of those pieces to make those holes is your fraction. Alright, so hopefully this is making sense. We're going to do one last example, and then I think we're going to have to wait for the next thing. The next thing is going to be, after we get through this one, is converting mixed numbers to improper fractions. So I was hopeful that we could get to that today as well. But what we're going to do is we'll just do one more example of going from improper fractions to mixed numbers, and then next time around we'll go from mixed numbers to improper fractions. We'll flip that arrow up top in the other direction. So the other improper fraction that we were dealing with earlier that we're going to pull back now is that 67 over 12. So you can solve this, once again, if you look at it, you can ask yourself, all right, how many times does 12 go into 67? And you could start counting by 12s, and you'll see eventually how many 12s you can fit inside 67 without spilling over. But if you don't want to do it that way, we can do it both ways if we're quick enough. What you can do is you can just break that 67 into groups of 12, which is going to be a little bit tricky because, you know, you have to do some subtraction and stuff in your head, or it's going to be a lot of lines of you writing. But what you'll get is that 67, just to save you a little bit of time here, is we're going to get that, all right, well, 67, if I break that into one group of 12, I'm going to be left with 67 minus 12, which is 55. Right? So far, no problem. I'm going to get rid of those up there, because I might need to use every inch of free space. So we've got 67 minus 12 equals 55. So after we've made this one hole over here, we're still left with 55 twelfths. Well, I could take another 12 out of that, right? I'm going to put that 12 over here. 55 minus 12 is going to leave us with 43. So at this point, we've made 2 wholes, and we still have 43 slices of pizza. I know I said I wasn't going to use it, but we still have 43 slices of pizza to go. So we can take another group of 12 out of there, make another hole. 43 minus 12 is going to leave us with 31. So now we've made 1, 2, 3 complete pizzas, and we have 31 slices left to go. So we'll make another group of 12. 31 minus 12 is going to leave us with 19. And we've got a 4th group of 12 over there, right? So we've got 1 group of 12, 2, 3, and 4 up there. Every time that we've subtracted 12, we've put that 12 over here, right? So far we've got those 4 groups of 12, and we still have 19 pieces of pizza to go. Now let's make a 5th group of 12, 19 minus 12. Oops. So we got another group of 12 down here. We've got that extra group of 12, so we've got 5 holes. And now we're left with only 7 pieces. So we can't make another whole pizza out of just those 7 slices because they're only each 1/12 of the pizza. So we're left with 7 twelfths. But right now we've just got this whole collection of fractions. But if you notice, this 12 over 12 here, that's just 1. This 12 over 12 here is just 1. This is just 1. This is just 1. And this is just 1. So basically what we have is we've got 1 plus 1 plus 1 plus 1 plus 1, which is 5, right? We've got 1, 2, 3, 4, 5 such fractions. Plus this leftover bit, this 7 over 12. And if we want to write that as a mixed number, we just get rid of that plus sign, and we make it 5 and 7 twelfths, like that. Alright, so that's one way that you can sort of go about it. The other way is you ask yourself, how many times does 12 go into 67? And here's the way that you can do that. I'm going to get rid of some of this up here. We're just going to go through it really quickly. This is kind of neat because this is something that you can get. You can get this entire mixed fraction by just doing long division. You can get the whole thing by doing long division. I'm going to erase the stuff in the middle. I'm going to leave that 5 and 7 twelfths at the bottom so that you can see what we're doing. And you can compare our answer. So we've got the 67 over 12. That's our starting point. So we've got 67 divided by 12. All right, now if you go through this, you'll get, well, 12 doesn't go into 6, so long division isn't actually that useful here. You still have to figure out how many times 12 goes into 67. So if we just count, we'll get, okay, 12, 24, 36, 48, 60, 72. 72 is too big. So we've got 12 times 1, 12 times 2, 12 times 3, 12 times 4, 12 times 5 will give us, 12 times 5 is equal to 60, which is going to go right there. And we subtract, right? 67 minus 60 is going to leave us with just 7. Now if you notice, we could have obviously kept going. If we wanted to do this with decimals and stuff, we could have made it 67.0 and then brought the 0 down and kept going. Or what we can do instead is we can say that we've got this remainder, right? We've got our quotient is 5, our remainder is 7, but if you look, our quotient of 5 is the number of whole pizzas that we can make out of 67 twelfths of a pizza. Our remainder becomes our numerator in our mixed number, and our divisor, our 12 that we started with, just comes along for the ride and becomes our denominator. So if you go through that long division thing, the divisor is your denominator, your quotient is your whole number, and your remainder is your numerator. Alright, so that's a lot of terms and stuff, but stare at it and hopefully you'll see what I mean with a question like this. We'll go through more examples when we have a bit more time, But in the next lesson, what we're going to do is we'll start with going from mixed numbers to improper fractions, which I personally find easier to sort of think about because it's a more it's a really straightforward process, and you can just sort of use that process anytime that you need to convert from mixed to improper. And then after that, we'll get into the nitty-gritty details of adding and subtracting fractions, which is the next big thing that we have to tackle. Sorry that this one's a little bit long, but hopefully you guys got through it all right, and I will see you in the next video. Have a good one.